First of all, thank you for the invitation to this really nice conference, and yeah, thank you to the organizers for arranging such a lovely conference. Yeah, so today I will talk about strategies for analyzing anisotropic data, and in particular anisotropic cosmography approaches for mapping the local universe. So first I will give an introduction to the field of cosmography, and then I will give a motivation for anisotropic cosmography frameworks. Then I will show you the explicit cosmography expressions for luminosity distances, and I will also briefly talk about cosmography for the cosmological drift effects, which are these more novel cosmological measurements that we have around. And then I will discuss things in the end, and in particular I will mention some things that you may want to think about if you want to apply cosmography to data in practice. Okay, so what is cosmography? Cosmography in the modern usage of the word by people like Weinberg and Matt Visser can be said to be the investigation of the universe through measurements without imposing restrictions of the field equations for gravity. So this allows us to map the cosmological kinematics while staying agnostic, while not assuming anything about the field equations or the energy momentum that we may have around in our universe. And this then allows us to extract information, model-independent information from the data. And so usual approaches to cosmography, while they don't make assumptions on the field equation side of things, they do make assumptions about the parameterization of the geometry, and in particular symmetry assumptions. So typically these frameworks are valid for the Friedmann-Lemaitre, Robertson-Walker, the FLRW class of metrics. And so now it's clear that if you want to map the universe that in the regime where there is not convergence, where we have not converged to isotropy yet, we want to break the FLRW symmetry somehow. And there are various ways to do this. We can do this in model approaches, like with employing exact solutions or perturbative frameworks for modeling the local universe, and then formulate observables within the given model, and formulate the cosmographic expressions. But there are also some approaches to cosmography that go even further and kind of in the spirit of cosmography that is model independent. They're going to stay agnostic, to not make assumptions, both for when it comes to the field equations, but also when it comes to the form of the space-time geometry itself. So if successful, this allows us to map the kinematics and curvature degrees of freedom of our universe, of our cosmic vicinity, as modeled independently as I think we possibly can. So that is an approach to cosmography that is ambitious, because you can imagine you introduce quite a lot of extra degrees of freedom when you go down such a path. But it's also really rewarding, and if successful, it means that we can potentially actually model independently, map the universe around us. So so these frameworks are not in contradiction to isotropic analysis or more model-dependent analysis, but it's a complementary tool that you can use to potentially extract more degrees of freedom from a cosmological survey. And in particular, the frameworks that I will show you can provide a theoretical basis to make more rigorous some of the investigations in the literature that pop up once in a while, where people are analyzing multiples, analyzing anisotropies in cosmological parameters in a phenomenological sense. And so these frameworks can provide a theoretical basis for these, and may improve these analysis. So what is cosmography in practice? So let's bring cosmography down to Earth. So cosmography is basically just a Taylor series expansion of cosmological observables around the observer. And so typically we use redshift as an expansion parameter in these approaches. And an example of cosmography that you would all know is the Hubble-Lemaitre law, where we expand luminosity distance to first order in redshift in an FLRW universe, and so we get a coefficient out, which is the Hubble constant in this relation. And this talk is basically about expanding a bit on Hubble's law, both potentially going to higher order in redshift, but also incorporating the anisotropics around us, so that we can, possibly explore the wealth of information that may be in these big cosmological data sets that we are going to have around. So let's start with luminosity distance. As many of you will know, it's a distance that's defined as the square root of the ratio of the intrinsic bolometric luminosity of a source and the flux of as observed from that same source. And this is a distance that can be measured if we know the luminosity of a source, or if we have sources that are standardizable in terms of their luminosities. So this is where standard candles and standard sirens are really useful as probes of luminosity distance. So let's look at how the cosmography for this observable look in an FLRW universe. This is a well-known result, and this formula here is taken from Matt Visser's paper. So at leading order, you will just have the Hubble law that you will all know, where the Hubble constant enters as the proportionality constant between luminosity distances and redshift when we are close enough to the observer. So when we go to second order, we have the deceleration parameter entering, which is the second time derivative of a scale factor, and it comes with a minus sign by convention. And as you will probably know, that this term here becomes important when the distance relation starts having concavity, and it's important for dark energy constraints in cosmology. And we can go to higher order, and we have the so-called jerk parameter entering, which is the third time derivative of the scale factor, and we also have a spatial curvature parameter entering, which is the Gaussian curvature of the spatial sections of the FLRW universe model. And so now it's clear that when we want to incorporate anisotropies, we have to break these symmetries that are built into this cosmographic expression. And as I mentioned to you, there are various ways of doing this. So we can take model-dependent approaches, but I'm going to focus on model-independent approaches, so doing things for an arbitrary space-time geometry in principle. And these approaches to formulating cosmic observables were pioneered by Christian and Sachs already in the 60s, and there has been later important developments, for instance, by the groups of Ehlers and George Ellis, and the groups of, for instance, Chris Clarkson and Roy Martins are also continuing to work on these frameworks. So in my work, I've basically expanded on these frameworks here. So the idea is that I want to formulate a luminosity distance cosmography that's valid for your given space-time geometry that you leave unknown, and so you want to define the appropriate cosmographic coefficients that gives you the right series expansion in your particular in the context of your given space-time geometry. And so a way to think about this is that we can think of this as a mapping of the usual cosmographic or cosmological parameters in FLRW to effective cosmological parameters that are valid in our given space-time geometry. And so these generalized cosmological parameters are now going to vary with the point of observation and also vary across the individual observer's sky. And they will do so in a particular way that depend on the geometry around them that you can then formulate if you write things down appropriately. So yes, I'm just going to outline the assumptions of my analysis here. So there's always assumptions also in model-independent approaches that we call model-independent. So here I make a rather minimal set of assumptions. So I assume a Lorentzian space-time and that geometrical optics applies for the light or gravitational waves that propagate in the space-time. We assume Etherington's reciprocity theorem for relating luminosity distance to angular diameter distance, and we assume a congruence description for the emitters that are around in our space-time, so the galaxies or stars that we would see in our astrophysical catalog. And this is basically just the smoothness requirements that gets rid of issues with singularities and so on. So when we assume this, and when we assume that luminosity distance is a well-defined function of redshift in our space-time, we get a cosmography that looks like this, where the effective Hubble parameter is now going to be given by the rate of change of photon energy along the photon null ray. So there's a sense in which when you start generalizing observables to more complicated and to arbitrary space-time geometries, there's a sense in which the inverse energy function plays the role of the FLRW scale factor on the observer's past light cone. So this is a quite natural observational generalization of the FLRW scale factor. And so you can see when we go to higher order, we have the second order derivative of the photon energy entering in the effective deceleration parameter, and so on, more derivatives when we go to higher order. We also have curvature entering explicitly in our cosmography through the what we call the effective curvature parameter here that replaces omega k in the FLRW framework, and so the curvature enters here through this Ricci focusing term, which basically just comes from the Sachs optical equations, where this term is present. Okay, so it can serve us well to look at the geometrical interpretation of these effective cosmological parameters. So what what do they actually tell us about the universe around us? So I think it was George Ellis who first in the 80s realized that there's this curly H function here was a suitable, effective generalized Hubble parameter, and realized that it could be written in this form here, where the idea is to do a multiple expansion in the direction of the incoming light. So E. So E here is really just the direction in which we see a galaxy or a star on our sky. So we can expand in that direction vector, and when we do that, we have a quite simple multiple decomposition, where at monopolar order we have the expansion rate of space around the observer. So this is a quite natural generalization of the FLRW Hubble parameter. That is what the FLRW Hubble parameter is telling us about in FLRW physics, how space is expanding locally around the observer. But now this variable, this expansion rate is now generally going to vary from observer to observer on account of breaking of translational invariance. So when we go to higher order, we will also see that we have higher order multiples just because we broke isotropy, and so we're going to have if our observers are non-geodesic for some reason, if we consider that, we have that 4 acceleration gives rise to a dipolar signature, and when we go to quadrupolar order, we have that the shearing of the observer congruence, the anisotropic expansion of our cosmic neighborhood, it enters. So it tells us that if the observer is looking along that direction where space is expanding more than the average direction on the sky, the observer will see an enhanced value in the inferred Hubble parameter through the leading order distance redshift cosmography. So yes, this is a quite natural generalization of the FLRW Hubble parameter, and you can play the same game going to higher order in your cosmography. And so what you will find is similar. There's sort of nice interpretable multiple expansions in the direction vector in which the direction in which we see the astrophysical source. And the important thing to note here is that these is that each effective cosmological parameter is truncated at a finite order in its multiples. So this truncation here, a quadrupolar order, it's not an assumption or truncation that I put in by hand. It's really the exact expression, and it does that we actually at each order in redshift we have a finite number of parameters to constrain. Of course, we have more parameters than in an FLRW model. So 9 degrees of freedom is more than 1 degree of freedom, but it's still quite remarkable somehow that we have, that we can actually formulate things in this very generic setting. We have not assumed anything about our space-time geometry. We can formulate things in terms of a finite number of degrees of freedom. So it means that if we can control the truncation of our series expansion, we in principle have a finite number of degrees of freedom to constrain, with which is ideally possible with a high with high precision measurements. Okay, we can also look at what happens at higher orders with the effective deceleration parameter. You don't have to understand all of these terms that are here in this hierarchy of multiples, but you can just see that there's the expansion rate again entering now with time derivatives and spatial derivatives, and you also have shear again entering also in quadratic terms. You have vorticity when there's rotational degrees of freedom around the observer. This also enters, and so on. So we can look at the first term here in the monopolar contribution. This is the local acceleration of length scales between, this term describes the local acceleration of length scales between test particles in our space-time. So this is also the only non-vanishing term in the FLRW limit, and that is why the deceleration parameter has its name. It is a parameter that measures acceleration or deceleration of space. And now, because you see that because you have this hierarchy of correction terms, the interpretation becomes much more involved when you are in another space-time, in an arbitrary space-time in principle. So this is something to have in mind when analyzing data model independently. All right, so you can look at the behavior of these cosmographic parameters in simulations. That's a good place to start if you want to test frameworks. So I've been doing this together with Haley McPherson in Einstein Toolkit cosmology simulations, and together with Julian Adamic and co-authors in the context of G-evolution simulation codes. And this picture here is from a 200 megaparsec scale simulation in the Einstein Toolkit, or the simulation box is much bigger, but the smoothing scale that we have applied here is 200 megaparsec. And this is the sky map of a fairly typical observer in this simulation. And so you can look at the cosmography that such an observer would ideally infer if we imagined placing like sources on the observer's sky. And so what you see here is you clearly see a quadrupolar signature in the effective Hubble parameter, which comes from the shear in the cosmic neighborhood of this observer. And so on, you can also analyze the higher order cosmological parameters. All right, so I think I'm just going to talk briefly about cosmological drift effects as well, because thank you, because distance measures are not the only measurements that we can do cosmography with, And I think that cosmological drift effects are particularly interesting observables to look at, and also quite interesting theoretically, I think. So cosmological drift effects are measurements in real time of changes to cosmic observables. So examples of this are redshift drift, where we measure the change in redshift of sources in proper time, in our proper time. So this is going to be probed with various transition lines in the hydrogen atom through the ELT and SKA. There's also position drift, where we track the change in angular position of a source in our proper time. And this has actually been measured to a quite high accuracy through proper motions of quasars measured by Gaia. So these cosmological drift effects are really fundamentally changing how we view observables in cosmology. So usually we think of observing on one instance of our light cone. So we are at one point in time, and we track our light cone back and view sources that intersect our light cone at various cosmic times. But with the cosmological drift effects, we are rather observing multiple instances of our light cone. So we are really considering that we have an extension of our own world line, and we are similarly considering extended sections of emitters, so galaxies, world lines. And so this gives us a quite non-trivial boundary value problem to solve for when we want to solve for these cosmological drift effects. And it makes them quite theoretically challenging to compute when you are not in a space-time with high symmetry as the FLRW universe models. But you can nevertheless do that, and I have a number of papers on this, in fact, where you can actually formulate equations a little bit similar to Sachs optical equations just for the drift effects. And so here I focus on the papers that I have also with Mikolaj Kosinski on formulating cosmographic expressions for these observables. So the exact expressions may not be too important. I guess the take-home message is that you can do cosmography with these observables as well. So you can actually, much like the expansion that you previously saw for luminosity distance, you can do a cosmographic expansion of redshift drift in redshift. And we can formulate this in terms of effective cosmological parameters, where we have here the effective Hubble parameter from before entering, and we also have a generalization of the FLRW deceleration parameter, which is then not the same generalization as you saw for luminosity distance. So that's a kind of a generic feature that when you start generalizing your space-time geometry, well then observables will not have the same generalization away from FLRW. So that's one way of testing alternative frameworks is through complementary measurements. Okay, so we can just briefly look at this effective deceleration parameter. It's again formulated in terms of a multiple decomposition. It looks a little bit more complicated because you also have this kappa entering, which is actually the position drift of the source. So there's a sense in which redshift drift and position drift couple, which is perhaps natural because the redshift drift depends on the kinematics of the source, and the position drift, essentially, that's one of the things that the position drift probes. So you're again going to have this hierarchy of multiples that's going to tell you about the kinematics, thank you, and curvature of your space-time. So we can just focus on a few terms here. You have the Ricci focusing term as the first term here, and the monopolar contribution, and it's the only term that survives in the FLRW limit, where all of these other terms are identically zero because of the symmetries. Here we also have an interesting term, which is the electric part of the Weil tensor, which is just the Newtonian tidal tensor in the Newtonian limit. That gives rise to a quadrupolar signature in redshift in redshift drift, for instance. Okay, so this is the expression for position drift at leading order. So again, we see that we have a finite number of multiples in principle to constrain if we have a precise enough survey, and they will tell us about curvature and anisotropic expansion degrees of freedom around us. So these are the sort of terms where curvature explicitly enter through the Ricci and electric Weil tensor and another Weil component. Okay, we've come to the discussion. So I guess the take-home message from this talk is that model-independent cosmological analysis of distance redshift data and of the cosmological drift observables are possible. In theory, at least, so these things are always dependent on, in practice, on the quality of our astrophysical catalogs. So we require a sufficient amount of statistics and sky coverage and control over our systematics in data. So now may be the time to start trying to implement these anisotropic cosmography methods, given that we are at a time where cosmological data sets are really exploding in quantity. Just for our supernova of type 1a catalogs, we are going to have several orders of magnitude growth of our data sets. We are also going to have access to these new cosmological measurements, such as the drift effects. So it may be a little futuristic at the moment to talk about anisotropic cosmography searches in these, but there may be a time where that is not futuristic anymore. So things to think about when applying cosmography to data. So we obviously want to think about the scale in our problem, so the scale of observation and the survey geometry that we have. So do we have sufficient data and sky coverage to constrain the relevant coefficients that we want to constrain in our cosmography? And if that is not the case, you may want to think about doing something in between a full model independent analysis and something that's completely model dependent. You could do something in between and sort of motivate various truncations of the series, or various simplifications within this framework. There's also convergence properties that are important, and obviously when you consider series expansions, and these have been investigated in quite some details for in quite some detail for the FLRW cosmography, but there has until very recently at least there has been almost like no investigations of this in other geometries. So I have work in progress together with Moak Hills, my PhD student, who has done some really nice work in exact solutions, and also together with Haley McPherson, who is doing work in numerical simulations. As a final thing, I think it's also important to say that we should, of course, always be careful when we interpret our results. So, a significant anisotropic signature in data is not necessarily in contradiction with lambda CDM, especially if you are at the very low redshifts. You may expect considerable anisotropies also in lambda CDM. So it's important to do a careful comparison study if you want to go into such investigations. So with this, I want to say thank you for your attention, and thank you again to the organizers.
Thank you very much, and perfect timing.
Oh,
so are there any questions for Asta?
To what extent is the inverse problem tractable? Suppose you have perfect measurements of the convergence, the acceleration, and the shear tensor. Can you get to a metric?
Yeah, that's a good question, actually. Reconstructing the metric from these combinations of combinations of kinematic and curvature variables that we have. Yeah, so that's an interesting problem that has actually been investigated. That has also played a role in the Ehlers-Gern-Sachs theorem for trying to prove the FLRW metric or the closeness to the FLRW metric from CMB observations. So I think it's that reconstruction problem is quite a complicated one. You typically want to make additional assumptions than what your measurements are directly telling you, at least in the context of Ehlers-Gern-Sachs theorems. But this kind of complementary measurements can give you, access to more geometrical information that can then, I think, bring you closer to being able to actually reconstruct the geometry.
Thanks very much. That was really interesting. I was wondering, given what you said towards the end about the interest in perhaps ratcheting the complexity of the model from something that is fully parametric down to fully generalized.
Yeah.
Do you have an idea, given the sort of constraining power from current surveys, how far you would be able to ratchet more degrees of freedom before you completely wash out all constraining power?
Yeah, so I did a little bit of a preliminary analysis on JLA and Pantheon data together with Suhail Dhawan and Haley McPherson and a master student that I had at the time, and what we found is that, you have to basically, I don't think that there's more constraining power than to go to the dipole and quadrupolar order at the moment, and even there you also have to preset the eigendirections to actually have enough constraining power. to say something, of interest. So yeah, but I think it's a really interesting time for instance, for supernova analysis. Is really going to help to have a couple of orders of magnitude more data. I think with this.
If there's no other questions, I might have a follow-up. Given what you were just saying about the different, or the first and second order, the dipole order and quadrupole orders, is there any indication from that preliminary analysis that including the higher orders changes or introduces or removes any sort of bias that you might see if you don't include those higher order terms? I was just wondering, given what you were saying, that if you include, say, the dipole and quadrupole orders, you might still be able to have constraining power at the level of current surveys from Pantheon and the other supernova surveys.
Yeah.
Is there any indication from that sort of preliminary analysis that including those higher order terms changes the inference?
So what we got in our analysis was basically a null result, in the sense that you could, if I remember correctly, so you could understand. There was nothing in those multiples that you couldn't understand in terms of the bulk flow estimates that were around for the surveys. In follow-up analysis by Suhail and Jessica Cowell, I think, and Haley McPherson, they interestingly found in an updated version of Pantheon, they found a significant quadrupole that didn't quite go away, even when incorporating bulk flow, corrections from bulk flow. So that's quite interesting, something to look more into, I think.
Is there one last question? Yes.
Hi. First, I would like to make a comment about the other question. I would say that actually not including the higher order introduces a bias. We do have some papers showing that if you truncate too early, you have introduction of bias in the lower order multiples. But I also have a question for you. Can you go back to the slide where you're showing the redshift drift?
Yeah.
So as long as I understand it, it's mainly very well driven by the far acceleration, right? So if you don't have any, if you assume that you have a geodesic flow, you have basically just the last term over there, right?
Yeah.
Do you have any idea of how, I know that it's the theory and observation, but do you have any idea of how long would it take to be able to measure that order of multiple in a redshift drift?
So I have not really attempted to do a forecast analysis. Because I'm fearing a bit for the result, I guess. I mean, redshift drift is already a futuristic measurement, and I think you need to know quite well, the instrumentation and how these measurements are actually being done, and so I think it really depends on the exact instrumentations and upgrades and so on that you choose to make in the future, how well you can constrain these things. But yeah, it's kind of optimistic to see that there's actually not so many terms here if you take the geodesic limit, which is a natural thing to do. And it's also quite interesting for the point of view of constraining alternative dark energy scenarios, because redshift drift is just really, really sensitive to the Ricci focusing term here. So it's a really good way of probing, in a clean way, violation of strong energy condition, where it's a bit more convoluted for other observables. So that makes redshift drift like a good model-independent probe. Yeah.
Okay, thank you.
Okay, let's thank Asta again.
Thank you.